Hi everybody, I'm the greatest living inventor, and today we are doing my invention, teaspoon passive cooling. I'll write it down. Teaspoon passive cooling. Okay, so first, what is it about? Excuse me, I'll take my shirt off. Okay, so I'm reading the description. Just like a silver teaspoon, just checking that you can hear me. Yeah. Just like a silver teaspoon protects a cup from breaking, in parentheses, when you pour boiling water into it, into the cup, close parentheses, so when a spacecraft enters the atmosphere, we can use a very conducting material that will conduct the heat to a radiator behind the spacecraft. In parentheses, instead of a ceramic heat shield, close parentheses. So basically it's an alternative to heat shield of a spacecraft, of a spacecrafts as you know, when a spacecraft comes back to Earth, it suffers a lot of heat. You remember that the Columbia space shuttle exploded because the heat shield was damaged. So it's really important that the heat shield will work, and it's critical. So this thing is instead of what we use today. It's I think it's better. Okay, and basically passive cooling is like they planned to use in the Lockheed Martin X-33. You can read about it if you look in Wikipedia in heat shield. Okay, in Wikipedia you can see there is a section about passive cooling. Okay, about passive cooling, and but my version is like improved. Okay, it's like the next generation of passive cooling. Okay, so what is my idea based on? First of all, let me describe what is the current idea of passive cooling. In short, if we have the spacecraft, let's make it round. So, and here are inside are the astronauts, and sitting, and they are coming back to Earth, and of course the atmosphere is here, and this goes down and rubs against the atmosphere and gets a lot of heat. It gets very hot. So currently a normal ceramic heat shield, okay, is made out of ceramics, and it's like here. Okay, it's attached to the spacecraft, but I want you to see that it's a separate thing, and it's attached to the spacecraft, and it just absorbs all the heat, okay, and it radiates, but it radiates like to here, okay, so it gets the heat and it radiates to the same place, so it's not really cooling. I mean, it more of absorbs. Absorbs, I'm sorry. Okay, so another method, this is a heat shield. Ceramic. Ceramic heat shield. Another approach is the passive cooling, which they never really used, okay, but it was supposed to be on Mercury. Mercury is the mission that they wanted to encircle the Earth, okay, with John Glenn, which he did, but they didn't use eventually passive cooling. So this looks like a tower, okay, so it's like something like this, and it has like beams, and all this is made out of something that like graphite, okay, this is graphite. And I'm describing now what was supposed to be on the X-33. Okay, so, and on the Mercury there was supposed to be something similar. So I'm not sure exactly what was supposed to be on the Mercury. I'm describing like a hybrid that looks like the Mercury, because in Wikipedia there is a picture of what was supposed to be in the Mercury, but wasn't eventually, and there is a description of what was supposed to be on the Lockheed Martin X-33. So both of them never used it, but I'm trying to describe what it was supposed to be. So it's graphite passive cooling. Okay, so what it means is it gets the heat, let's draw it in brown. Okay, so it absorbs graphite, passive cooling. It absorbs the heat and radiates it, let's say more accurately, it absorbs the heat here and radiates it here. Okay, so you see it's not much of a difference because the heat still touches the vehicle. Okay, this is the vehicle, the spacecraft. So if you absorb it here and radiate it here, and then the vehicle comes, then you didn't do much. Okay, so now that we've seen what exists or was supposed to exist, and mostly this exists, so now I'll describe my idea and what it's based on. Here is a rough translation from page 105 of a Hebrew book called Physics for Your Enjoyment that I read many times as a kid. It's by Y. Perelman and it's published by H. Froynd. Okay, just let me write it down so it's, if you want to find it, you can find it. Physics for Your Enjoyment. By Y. Perelman and published by H. Froynd. Okay. So in page 105, I'm translating. This is what they write. What he writes. An experienced housewife. Just see if I can show you the book here. Okay, I didn't plan to show you this, but this is the book. Okay, so it was a series. I think I also have the chemistry one. Okay, so any experienced housewife has the habit of inserting a teaspoon into a glass made of glass, okay, a drinking glass made of the material glass, before pouring hot tea into it. And this is in order for the glass not to crack and break. What is the physical basis for this? Why ever should hot water shatter a glass? A glass made of the material glass. The answer is simple. When you pour hot water into a glass, its walls are not warming up all at once. At the beginning, the inner layer is warming. Okay, so 15 minutes. Okay, so if we have a glass, So this is like theoretically what a glass looks like, but in practice it has some width. Okay, so it's like this. So if we pour hot water, let's say, I don't know, some hot liquid like coffee or tea, okay, let's think of it like in infrared. So this becomes hot, and also the bottom becomes hot. But the but the outside is still cold. Okay, all this and also all this, but I'm too lazy to draw, is still, let's draw it anyway. Okay, so this is the glass in, if you see it in heat, if you see the heat in infrared goggles. So you see that this becomes hot, but this didn't have the internal side, the inner side became hot, but the external side did not have time to get hot. So the red inner side expands, but the outer blue side doesn't have time and it breaks. Okay, they don't move together. Okay. The answer is simple. When you pour hot water into a glass, its walls are not warming up all at once. At the beginning, the inner layer is warming, the red, while the outer layer remains cold, the blue. The inner layer then that warms expands at once before the outer layer had time to absorb heat and expand too. Therefore, the inner layer is pressing the outer layer very forcefully until it is disengaged from it and the glass breaks. You might think that in a glass with thick glass walls, there is less danger of shattering. Actually, the opposite is true. Glasses with thick walls tend to shatter more than thin-walled glasses. The reason is that the thin wall warms entirely faster, and so both its sides are expanding almost simultaneously. Thick-walled glass, as opposed to this, warms relatively slowly. When you are buying thin-walled glasses, make sure that the bottom of the glass will be thin too, because the bottom of the glass warms first and faster. A thick-bottomed glass will shatter very quickly under the influence of sudden heat, even if its walls are extremely thin. Chemists use glass flasks with very thin walls and bottoms. With this, they can boil water directly on a burner. Okay, so you know that a chemist flask looks like this, and it's thin here and it's thin everywhere. So you can put a flame below and and it expands all at once. So if there is the water inside, it doesn't explode. The glass doesn't break. Okay, the ideal flask will be, of course, the kind that will not expand at all in the influence of heat. The quartz crystal comes very close to this. Its expansion is 15 to 20 times smaller than the expansion of glass in similar conditions. A flask made of transparent quartz crystal, okay, quartz, crystal, the material that is in sand. A flask made of transparent quartz crystal with 3 thick walls will not shatter in the influence of heat, even if it will be inserted while it's white hot into an ice bath. In parentheses, quartz flasks are convenient for lab use also because of the relatively high melting point of the quartz, 1700 degrees Celsius. Okay, so quartz is 700 degrees Celsius. Its melting point. It becomes liquid in that high temperature. The reason to this is partly because of the good heat conducting of the quartz. Okay, so quartz, if you have a piece of quartz, then if you heat one side of it very, very quickly, the other side will be hot too. And if you cool one side very, very quickly, the other side will be cold too. So this means conducting very well. The reason for this is partly because of the good heat conducting of the quartz, which far surpasses that of glass. Glass glasses shatter not only in rapid heating, but also in rapid cooling. This time the reason is a quicker contraction of the outer layer that presses the hotter inner layer. Okay, so if you put this in the refrigerator, then it's the same. Okay, so a careful housewife will never insert a jar full of a jar or jug, a pitcher full of boiling concoction into the refrigerator. So if you have a jar of hot coffee, you don't put it in the refrigerator because it will break. Okay, because the outside will become cool while this is all hot, and it doesn't have time to become cool, and then it breaks. Let's go back now to the teaspoon. To my the basis to my idea. How does it protect the glass from the danger of shattering? Okay, if you put a teaspoon before you pour the hot tea or coffee. When you pour boiling water into the glass with the spoon inside it, the teaspoon warms up very quickly. As opposed to glass, the metal teaspoon is a good conductor of heat. As a result of this, the water loses some of their heat and cool to a degree which is not enough to damage the glass. Okay, so if we put a teaspoon inside, okay, this is a teaspoon, and we put it in advance, and then only put the this hot water, what you see in red, then this becomes red very gradually, okay? Because what becomes red in the first place is the spoon. In the beginning, this is blue. Like all the glass, and the teaspoon becomes red. Okay? The teaspoon is a very good conductor of heat, and it becomes red, and then it radiates all the heat to the environment, to the air. And then this becomes less hot, okay, so all this, because of the radiation, becomes less hot, the coffee or the tea, and also the teaspoon, of course, becomes, first the teaspoon becomes less hot, then the okay, and this becomes hot gradually. Okay, this becomes hot, and eventually everything becomes more or less hot, the same temperature in the same time. Okay, it spreads the time, it lengthens, make it longer. It makes it the time that it takes for the glass or the cup to change its temperature longer. It lengthens the time. So if we put the spoon, the cup doesn't break. Okay. So let's go back now to the teaspoon. Sorry, let's see what time is it. 27 minutes and something. Okay, let's go back now to the teaspoon. How does it protect the glass from the danger of shattering? When you pour boiling water into the glass with the teaspoon inside it, the teaspoon warms up very quickly. As opposed to glass, the metal teaspoon is a good conductor of heat. As a result of this, the water loses some of their heat and cool to a degree which is not enough to damage the glass. During the same time, the walls of the glass warm up, and when more boiling water are poured in, the glass is no longer cold as it was in the beginning, and it's ready to accept them. Okay, so they described it a lot better than I did, but you understand the general idea. There is a few stages. Okay, first this is very hot, and then the glass is not hot, and then the glass is tepid, like lukewarm, not warm and not cold, and then we pour more hot water, but now it's closer to the temperature of the glass. So you understand it's averaging the temperature. This is hot, this is cold, and it brings them closer together. Ready to accept them. A silver teaspoon, okay, if this is a silver teaspoon, not a normal stainless steel teaspoon, a silver teaspoon is extremely good in protecting glasses against fast warming because silver conducts heat better than any metal. A silver teaspoon heats up so fast that it's hard to or impossible to hold it after the tea was poured without getting burned. Okay, it gives out a lot of heat. A copper teaspoon, okay, on the other hand, another material, copper, heats up slower, That's how you can distinguish between silver teaspoon and the copper teaspoon. The slow expansion of the glass walls is a nuisance in addition, to drinking glass made of glass, also in important parts of a water heater, boiler. Okay, so if you put water to hot water so you can shower, so the boiler that makes the water hot also suffers from this. The water gauge that indicate the height of the water surface level in the boiler is under a considerable pressure of steam, and so they tend to shatter much more. To avoid such danger, it's customary to assemble their walls from two layers made of different kinds of glass, with the inner layer having a smaller expansion factor than the outer glass. Okay, that's it for the children's book, okay, what I've shown you. Now let's see how it can apply to spacecrafts. The closest thing to what I mean that I could find was this. Okay, now I gave you the Wikipedia link to passive cooling in a heat shield, Wikipedia heat shield, and then the section about passive cooling. The current heat shields, ceramics, the same material is insulating, not conducting, and then radiating, emitting the heat in the same place. Okay, so it takes the heat and gives the heat in the same place. My suggested system, on the other hand, conducts the heat from the front, in terms of flight direction of the spaceship, to the back of the ship. And there you have a long radiator that spreads the heat where it's cool. It's like the end of the teaspoon that is in the open air above the glass. Okay, so my system looks like this. So let me draw it. Again, the same spacecraft, but now let's paint it in green, just so it's a different color. I'm sorry. This takes the heat. Okay, so there's something here that takes the heat, which is not attached. It's attached, of course, to the whole spacecraft. It cannot fall from the spacecraft, but it's like encircling the spacecraft, and from all sides. Okay, like from the front and back and the sides, from all around. And then here it has this something like this. Okay, so something like this. It doesn't have to be crossed beams. It can be like something like a radiator, but something that radiates heat. And then if we have, I'm sorry, let's call it teaspoon shield. Or maybe not shield, because it's not a heat shield, it's like passive cooling, but another kind of passive cooling. So and if the heat gets in here, okay, more precisely it comes in here, but I don't have room to draw it. So imagine it comes from here. So, okay, let's erase it and do it again. So the heat comes from here, and it radiates here, okay, behind the vessel. Okay, so it doesn't matter how much heat comes in here, it goes around from all the encircling arms and radiates from above the vessel. So the vessel goes down, and the heat radiates behind the vessel. Okay. So like the teaspoon that is in the open air above the glass. So this is like this. Okay, so now I give a suggestion of what the material of this should be, which wasn't available when they did this in the 1990s, and certainly wasn't available when the mercury was being done. So I'm giving you a link to hyperphysics.phi. I'll give you the link. And thermal conductivity of silver, 406 W, I guess it's watt, per meter Kelvin. Kelvin is the temperature, the absolute temperature. So thermal, let's erase this. Thermal conductivity of silver is 406 some units, W divided by M, I guess it's meter Kelvin. And we don't care what it is, it's some unit, okay? And watt is usually power, and meter is the distance, and Kelvin is the temperature, so it makes sense, okay? So if there is a lot of power over a short distance that passes, and in a large heat, because if it's cold, then everything is a good conductor. Everything becomes a superconductor, but when it's hot, then it's hard. So it's so this makes sense. Okay, so and as opposed to this, not supposed, but even more than this, thermal conductivity of carbon nanotube networks, which I took from Springer. I will give you the link. Thermal conductivity of carbon. Carbon and graphite is the same, but here it's in the shape of another molecular structure, carbon nanotubes, which wasn't available back then. Nanotubes. Nanotube network I don't have room to write it, that's why I'm writing it down. It's supposed to be carbon nanotube network, and its value is very, very high. It's 6,600. 6,600 of the same units. So you see it's like, I wrote how much bigger it is, 16 times better than silver. Okay, this is depending on how it's arranged, but it's a very, very high value. So nanotubes made of carbon are very light and strong and has superb heat conduction. 16 times, okay, 16 times. Better than silver when built in a specific structure. So this is the ideal material that we know today. So so that's it. That's my idea, to build a shield like this, but made of this new material. So and it's meshed together, so we don't have to make long nanotubes, which we cannot currently make a long tube. We can make only small tubes, but this is a network, so we can it's like a fabric. We can weave them together, and it works. It will conduct the heat. So that's it. So thank you very much, and I'll see you in my next invention. Thank you very much. Bye bye.